This is Physics 2120, Lecture 29. Today we're going to start talking about interference of light waves. So wave optics is a study concerned with phenomena that cannot be adequately explained by geometric optics. Those include such things as interference, diffraction, and polarization. Now if we remember from last semester when we talked about wave motion, constructive interference, the amplitude of the resultant wave is greater than that of each individual wave. Destructive interference, the amplitude of the resultant wave is less than that of either individual wave. And all interference associated with light waves arises when the electromagnetic fields that constitute the individual waves combine. So to observe interference in light waves, the following two conditions must be met. Number one, the sources must be coherent. That means they must maintain a constant phase relationship with respect to each other. And number two, the sources should be monochromatic, which just means that the light has a single wavelength. So light from a monochromatic source is used to illuminate a barrier. Let's say the barrier contains two narrow slits, and the slits are just small openings. The light emerging from the two slits is coherent since a single source produces the original light beam. This is the most commonly used method. So if I have light coming as a plane wave and it strikes these two small slits, from Huygens' principle we know that the waves spread out from the slits. And the divergence of light from its initial line of travel is called diffraction. Now Thomas Young in 1801 first demonstrated that light waves can interfere from two sources. So he illuminated light on a barrier and he had two slits. And as the light comes through the slits, each one of them, from Huygens' principle, has a spherical wave that comes out from the slits. So they're acting as the source of the waves. So the waves emerging from the slits originate from the same wavefront, and therefore they're always in phase with each other. So the light from the two slits form a visible pattern on a screen. And the pattern consists of a series of bright and dark parallel bands called fringes. Constructive interference occurs where a bright fringe occurs, and destructive interference results in the dark fringes. So for example, if I had a light wavelength, maybe 400 nanometers, so purple light, and it was coming through. As the light came through, each individual one is going to form these circular wave patterns coming out. And we see where they trough and a crest cross along this right here, we get destructive interference. But where we get crests lining up when they're in phase with each other, we're going to get constructive interference. Now you can even see that in waves from the ocean coming and hitting these barriers out in the ocean. These openings act like slits, and as they come through we're going to get some places where there's destructive interference, so there's not a lot of wave motion, and so we don't have a lot of erosion, and constructive interference where the waves get bigger and we have a lot of erosion. So how does this work? As the light is coming through the two slits, they're in phase with each other as they come through the slits. If they travel the same distance to point P, they're going to arrive in phase with each other, and therefore we're going to get constructive interference. Now, as we move down from the center to the next bright fringe, that's going to correspond to this wave actually traveling exactly one more wavelength than the bottom wave. So if it's exactly one more wavelength, they're going to be in phase again, and we're going to get a bright fringe at that position. Now halfway in between, as this light comes here, and this one's traveled a half a wavelength more. If it's a half a wavelength more, then they are exactly 180 degrees out of phase. So when we add them up, we get 0, and that corresponds to a destructive interference or a dark fringe. Now if I look at the geometry of Young's double slit experiment, the path difference, or delta, is found from this tan triangle. Delta here, which is the difference in paths, R2 minus R1, is just d, where d is the distance between the two slits, times the sine of the angle that I'm going up here. This is going to assume the paths are parallel. It's not exactly true, but it's a very good approximation if L is much greater than D. For bright fringe produced by constructive interference, the path difference must be either 0 or some integral multiple of the wavelength. So the path difference, which is d sine theta for bright fringes, it has to equal m lambda, where m can be 0, plus or minus 1, and 2. M is called the order number. So, in the center, where m equals 0, is the 0th order maximum. And then when m is equal to plus or minus 1, they're called first order maximums, and so on. When destructive interference occurs, a dark fringe is observed, and this needs the path difference to be an odd half wavelength. So the path difference, which again is d sine theta for dark, is going to be m plus another half a wavelength, where still m can be 0, plus or minus 1 or 2. The position of the fringes can be measured vertically from the 0th order maximum. Now we're going to make some assumptions here that L is much bigger than the distance between the slits, and that D is much bigger than the wavelength of light. We're also going to use an approximation that we're far enough away that theta is small, and therefore we can use a small angle approximation that tangent of theta is essentially the same as sine theta. So y, the distance between the slits, is L tan theta, which we'll just say is L sine theta. We can see down here at this table, at 10 degrees, sine of theta is 1.7364, and tangent is 0.1763. It's a little bit off. At 5 degrees, they're even closer together. It's a good approximation for small angles. So d sine theta is equal to m lambda, and y is equal to L sine theta, so the distance between the bright fringes is lambda L over d times m, or for dark fringes it's lambda L over d times m plus a half. Now Young's double slit experiment provides a method for measuring the wavelength of light. This experiment gave the wave model of light a great deal of credibility. It was inconceivable that particles of light could cancel each other in a way that would explain the dark fringes. So let's use this. We say we have a viewing screen separated from a double slit by 1.2 meters. The distance between the two slits is 0.03 millimeters. The second order bright fringe, m equals 2, is 4.5 centimeters from the center line. Determine the wavelength of the light and calculate the distance between adjacent bright fringes. So first, find the wavelength of light. We know L is 1.2 meters, m is equal to 2, d is equal to 0.03 millimeters, and y bright is 4.5 times 10 to the minus 2 meters. So we take our equation, we solve for wavelength, we plug in our values, we get that the light is 5.6 times 10 to the minus 7 meters, or 560 nanometers. The distance between the fringes, and the distance between fringes would be y of m plus 1 minus ym, which is going to be lambda L over d times m plus 1 minus lambda over d times m. The m's go away. So the distance between fringes is just lambda L over d. And again, we plug in our values, and we get 2.2 centimeters. Now the bright fringes in the interference pattern don't have sharp edges. The equations that we developed give the location of the centers of the bright and dark fringes. However, we can calculate the distribution of light intensity associated with the double slit interference pattern also. To get the intensity distribution, we're going to make some assumptions. The two slits represent coherent sources of sinusoidal waves. The waves from the slits have the same angular frequency, and the waves have a constant phase difference. The total magnitude of the electric field at any point on the screen is the superposition of the two waves. So the magnitude of each wave at point P can be found. E1 is E0 sine omega t, and E2 is E naught sine omega t plus the phase difference. Both waves are going to have the same amplitude. So the phase difference between the two waves depends on their path difference. So delta is R2 minus R1, which we said was d sine theta. A path difference of one wavelength corresponds to a phase difference of 2 pi radians. So a path difference of delta is the same fraction of lambda as the phase difference of phi is of 2 pi. So in other words, phi over 2 pi is delta over lambda, or phi is equal to 2 pi over lambda times delta, which is 2 pi over lambda times d sine theta. The magnitude of the resultant electric field comes from the superposition principle. The electric field at point P is the electric field due to 1 plus the electric field at 2. So we are adding these two signs. We can also express this using some trigonometry as 2 E naught cosine phi over 2 sine of omega t plus phi over 2. So E has the same frequency as the light at the slits, and the magnitude of the field is multiplied by a factor 2 cosine phi over 2. The expression for the intensity comes from the fact that the intensity of a wave is proportional to the square of the resultant electric field magnitude at the point. The intensity, therefore, is I is equal to whatever the maximum is times cosine squared of phi over 2. It's going to be pi d sine theta over lambda. Or using our approximations for sine theta, it's I max, and it's going to go like cosine squared pi d over lambda L y. So the intensity is going to go like cosine of y squared. And sure enough, if we were to plot this, this is cosine squared function. This has a certain maximum intensity, and the period is 1 wavelength. And this is exactly what we see. We see it's 0 here, and it gets brighter and brighter and brighter and brighter, and then we reach a max and back down and up and down. Now this result is valid only if L is much bigger than D and for small values of theta. Now the sinusoidal wave can also be represented graphically by a phasor of magnitude E naught rotating around the origin counterclockwise with an angular frequency omega. So E1 is equal to E naught sine omega t. Makes an angle omega t with the horizontal axis, and E1 is the projection on the vertical axis. It's very similar to how we use phasors in AC circuits. The second sinusoidal wave, E2, is E naught sine omega t plus phi. It has the same amplitude, same frequency as E1, but it's out of phase by a factor of phi with E1. So the resultant is the sum of E1 and E2. So ER is going to rotate with the same angular frequency omega, and the projection of ER along the vertical axis equals the sum of the projections of the other two vectors. Now from geometry at t equals 0, ER is equal to 2 E naught cosine alpha, which is 2 E naught cosine phi over 2. The projection of ER along the vertical axis at any time t is given by this equation, which is 2 E naught cosine phi over 2 sine omega t plus phi over 2. Now with phasors, I can find the resultant of several waves. So I have 4 different waves that are all out of phase with each other by a factor of phi. Say I have 4 slits. I can do this problem just as easily using phasors. We just have to remember to maintain the proper phase relationship between one phasor and the next. The resultant phasor is the vector sum of the individual phasors. At each instant, the projection of ER along the vertical axis represents the time variation of the resultant wave. The phase angle alpha is between ER and the first phasor. The resultant is given by the expression EP is ER sine omega t plus phi. So ER is going to be a maximum when the phase difference is 0, 2 pi, 4 pi, and so on. The intensity is also a maximum at these points. And it's 0 at phase difference of pi, 3 pi, 5 pi, which the intensity is also 0 at these points. And so those results agree with the results obtained in the previous examples. So we can see this graphically. The phase difference is 2, so the path difference is 2, then ER is just equal to 2 E naught. As I increase my phase difference, we're going to lower the resultant until I get a phase difference of 180 degrees. When I'm adding these two, I get total destructive interference. And if I increase the phase difference again, eventually, when the phase difference is 360 degrees, my ER is at a maximum again. So for a 3-slit interference pattern, we'll assume 3 equally spaced slits. The fields are E1 is E naught sine omega t, E2 is E naught sine omega t plus phi, E3 is E naught sine omega t plus 2 phi. We can use the phasor diagrams to find the resultant magnitude of the electric fields. So the phasor diagram shows the electric field components and the resultant field. The field at P has a maximum value of 3 E naught when phi is equal to 0, plus or minus 2 pi, or plus or minus 4 pi. Those points are called primary maxima. Total destructive interference occurs when the wave from all the slits form a closed triangle. The field at P then has a value of 0, and those are at 0, 2/3 pi, 4/3 pi, etc. We can see this graphically. When the phase difference is 0 in all of them, I get the maximum value of the resultant electric field. And then as I increase the phase difference, we see this starts to shrink down. At the phase difference of 120 degrees, I form a triangle, and so I get no resultant vector. And then I continue to increase it to 180 between each one, and now 2 of them will cancel out. I end up with just the 1, and I get again another maximum because I've gone from 0 up to something, but it's not as big as the initial maximum. So as I plot this, here I have 3 slits. I get the primary maximum and secondary, primary, secondary, primary, secondary, as opposed to just the primary when I get the double slit pattern. The dotted line is a single slit envelope, which we'll come to next time we talk. But as I add, every time I add a slit, I'm going to get an additional secondary maximum. So for n slits, the primary maxima is n squared times greater than that due to a single slit. Notice that the more slits we have, the sharper these peaks are going to become. So as the number of slits increases, the primary maxima increases in intensity and becomes narrower. As the number of slits increases, the secondary maxima decrease in intensity with respect to the primary maxima. As the number of slits increases, the number of secondary maxima also increase. The number of secondary maxima is always n minus 2, where n is the number of slits. So, to review what we talked about today, we talked about interference, talked about diffraction patterns, and Young's double slit experiments and the conditions for maximum and minima. We talked about using phasors to figure out the intensities, and we looked at multi-slit patterns.